Hello, everyone. Welcome back. So the topic today that I'm going to talk about is light and physics. So what does this mean, light and physics? What does this mean, light and normal? So I designed and made this license because when I prepare for the spectroscopy, the characterization techniques, that I think I need to introduce about the life and physics. So I made this video especially to help to understand when I'm trying to explain the spectroscopy techniques. So what is the life and physics? Let's talk about the main source of light on our planet. So the main source of light on our planet is coming from the sun. So the sun is the nuclear fusion process. So the four hydrogens are fused into the heliums. So in that fusion process, there are suns release all the mass in the fusion process, and this released mass is converted into the energy, and this energy is coming to our planets as it light. So when you take a look the sunlight, you could see it's like a white color. It's really white color or not. So when this white color is passing through the prisms, then you will see the band of the light. So this you can see the spectrums in different color in the order of the violet, indigo, blues, green, yellow, orange, and red. So this is the dispersion of the white light into the different color. So this is called the light dispersion. So because the white light contains a large range of the spectrums from the violet to the red color. So this is what we call the visible spectrums. So the visible spectrums have the violet, blues, greens, yellow, orange, and red. So for example, violet have a wavelength of 380 to 440 nanometer. So we now know the wavelength, which is the distance between the two peak of the wavelength. So the shorter the wavelength is giving the violet, and the longer the wavelength, it's the red color. So the red colors, the approximately 700, you can easily remember the violet, which is about the 400 nanometer. So that's the average. So visible spectrum is between 400 nanometers to 700 nanometer. So this is the visible spectrum. So as we expand this visible spectrums more than this range of the wavelength. So what we are going to see is the solar spectrums. The solar spectrums have three different regions. The first one is UV, ultraviolet region. The second one's visible region, so that what we know before. And the third one is the infrared region. So in the visible regions is from less than 400 nanometer in wavelength, from 400 nanometer to 100 nanometer. This is the ultraviolet regions. So this region is very harmful for our human beings, because leading to the happening of the cancer. So this is about physics and biology. So this biophysics is a very great topic to talk about this about these regions and the interaction with these ultraviolet lights and our human being cell. This more into the atomic scale. The second ones that we already mentioned before is about the visible radiation between 400 nanometers to the 700 nanometer approximately. That is what we could able to see with our naked eye. And larger than 700 nanometer, which is the infrared radiations. So this is the higher wavelength. So it's could be anti-average to 1 millimeters in the wavelength. So if we are going to expand more than solar spectrums, not just into the three regions, what about the other regions? So what we call it the electromagnetic spectrums that we know about before: infrared regions, visible region, and ultraviolet region. So these are three regions that we know before. So left hand, the higher, larger wavelength than the infrared regions, which is from the 1 millimeter from 1 millimeter to the 10 millimeter. It is the microwave that we know that's using in the kitchen to heat the food, right, before we are eating. And also the radio wave is a very large wavelength that's using for the transmission of the informations, telecommunications, because these larger wavelengths can travel to one place to another to the very long distance, but allowing us to transmit these informations from one place to another. So this is the radio wave. And less than ultraviolet rate, less than 10 nanometer, which is the X-ray. The X-ray is what we are using now in the hospital. That's to see the ceramic bone structure of the human body. So that is very useful, but that is also dangerous if we are exposing so many frequently time or this as well. That's could leading to the other side effects because it is the very radiated and energy high radiation. Another one is the very high radiation, so it's a gamma wave. So this gamma wave is very highly radiated energy, so that is very harmful to our human being. So this is about the large range of the electromagnetic spectrums. Currently, what we could able to observe in science, it could be larger than more exponent this range of the wavelength. So mostly now we're talking about the wavelengths, the wavelengths for the explaining the electromagnetic spectrum. So what are the other relationships with the frequency, the energy with the wavelength? So this is a very good equation that we could able to explain about the relationships between energy, the wavelength, and frequency. So one you could able to see if that the smaller the wavelength, the higher the frequency and the higher the energy. And if the higher the larger the wavelength, the smaller the frequency and the smaller the energy. So this is the relationship between the wavelengths and frequency energy. And you could see this equation, the energy is already proportional to the frequency of V, the H is the Planck's constant, and C is the velocity of the light in the and also the lambda if the wavelength. So the wavelength, it's inversely proportional to this velocity, the energy of the wavelengths. So in this case, this is how we are trying to explain about the electromagnetic spectrums in terms of the wave. So life in terms of the wave nature. So how do we know about this light have a wave nature? So we do the experiments, which is called the best slit experiments. Long before the one scientist did the experiments, so they produce the light. This have the one particular wavelength and passing through the two slits. This is the one slit, this is the two slits. So after the light passing through the slits, there will be diffraction of the light. So this is the diffraction of the light. It's these two slits, okay? And then diffraction is coming from these two slits. There will be the interference of this diffraction. If the interference is constructed, there will be bright area. This is the constructed interference. And if they are distorted, there will be dark area in this region. So this is how I'm explaining the light having the wave nature. Okay, so this is coming from the interference pattern. So I need to explain what is the constructed interference and the distorted interference. So there is a two wavelengths, so which is the blue wavelength and the green wavelength. So if the blue wavelengths and green wavelengths are on the same place to each other, like the peak of the wavelength match each other, the red wavelengths will be constructed, the amplitude will be higher. So if these two wavelengths are in the opposite sides, they will be cancel each other. So this red line will be the straight line because this the blue wavelength and the green wavelength one cancel each other, and it will be the distorted interference. So the constructed interference will be higher amplitude, and then we will see the bright color. And then distributed interference, we will see the dark color because they will cancel each other. So this is how we are trying to explain the life of the wave nature. This is not just wave nature. What about the other natures? Light could be in the particle-like nature. In this case, we could able to explain by using the same experiment, just like the double-slit experiments, but in this case, we're trying to use the photon guns. The photon guns was going to emit, we're going to fire the photons in the quantum mechanical. It is the a packet of energy, like a particle nature of the light. But how we're going to try to explain is that here we're going to the photon guns, and this photon guns was going to emit light after photon, and then we will see there will be like a wave-like interference, just like before. This is the constructed interference in the wave-like nature. So that's why we will see the bright area around these regions, and this is going to be the dark region. So if you fire, okay, so these photons in both slits, sorry, so we will see that the appearance of like a wave-like interference pattern. And also, not just by the experiments, the Einstein had hypothesis when phenomena that's able to explain clearly more about the light have a particle-like nature using the photoelectric effect. The photoelectric effect, it's there is a incoming light. This is an incoming photon because photon is a light, light is a photon. So the incoming photons is going to hit the one's objects, like having the objects have the particle, the atom. So if this incoming photon energy is higher than the binding energy of the electron that is orbiting around this nucleus, and it's because of the higher energy, the electron will be kicked out because it's a smaller binding energy than this incoming photon energy. And then we will see there will be the kicking of the electron. So in this case, that we will consider the light internal of the photons like a particle-like nature. So that's key, that could be able to kick out the one's electrons in the inner shell or maybe outer shell of the atom. Okay, and then if this one is like a hole, there will be the jumping down of the one's electron from the outermost shell, and then there will be the emission of the radiations like a light, like a photon. This is the photoelectric effect. So when this electron is keeping out by this incoming photon, thus we will call it the proton electrons. So the electron is emitted in this manner, we call it the proton electron. In this case, we can see the light could be the wave-like nature or the particle-like nature. And the Einstein said that, okay, it seems as thought we must use sometime the one theory and sometime the other theory. Once at times we may use either. But we are facing with a new kind of difficulty because we have two contradictory pictures of the reality. Spikes using neither of them fully explain the phenomenon of light, but together they do. So what the Einstein want to talk about is that it is not complete explanation that the phenomenon of light just only by one's nature of light, just only by wave nature or just only by particle nature. But as we use this wave light and particle light nature, the wave particle nature of a light, we can explain the phenomena of light, fully understanding. Okay, so in this case, how is going to explain this wave light particle light nature together? And let's see. So the blue light and the red light, the blue light, which having their 700 and 470 nanometer wavelength. The red light is 365 nanometer. So this is the wavelength. Different wavelengths is giving the different color. blue color 470, red color 365. So we know now about the wavelength and energy relationships. So the blue color have a one particular energy, red color have a particular energy. So this can explain, okay, different wavelength have a different energy than different particular light. And then, okay, so now we understand the energy of the different color of light. So how are we going to understand the intensity of light in this fourth cycle? This is the red color. So intensity of light, how is going to understand it? In this case, we need to use the light in terms of the particle nature. The number of the particle could be the intensity of light. So let's see how the intensity of light can be increased by the number of the photon. So let's see when we are going to put the smaller intensity to the higher intensity, then how increased it is. Then when we are putting this small intensity of light together, then the light intensity is increased. Then more than when we are putting more this together, then the intensity of light is increased. That's because the number of photons in a beams are increased and the intensity increase. But this is the same energy, same wavelength. So that is the same color, right? So that's why the frequency of light or the wavelength of light or the energy of light could be the energy of each photon carrier, but intensity of light could be the number of photons in a beams. This how I explain light could be in a wave nature, light could be a particle nature. I think I hope you understand very well light could be the wave nature and particle nature. Thank you very much.